Hi, I'm Shinibali and I work at Cruise as a quantum physicist. In the previous video, we discussed how to use the Cruise toolset for optimally controlled state preparation of CAT qubits. In this video, we will discuss Wigner tomography simulations for CAT state readout using the Cruise toolset. Let's take a quick recap of the schematics of the hardware setup for the tomography apparatus for CAT qubits, shown in green over here. The cavity and the transmon interacts via the cross-Kerr coupling term. After the creation and manipulation of a CAT state in the CAT cavity, the protocol works as follows. One applies a Ramsey sequence consisting of two Ry pi by 2 pulses on the transmon with a delay time of pi over the cross-Kerr coupling strength. And during this delay, the cross-Kerr interaction acts like a controlled phase rotation with the CAT qubit as the target. In the end, one reads out the transmon by post-selecting of its ground or excited state, thus extracting the odd or the even CAT state. The corresponding Hamiltonian consists of the number operator for the CAT and the transmon mode, the self-Kerr terms for each of these modes, the cross-Kerr coupling term between the CAT and the transmon, an X drive connected to the transmon, and a Kerr correction drive connected to the CAT cavity. For this simulation, we instantiate a transmon class with its corresponding specifications from the hardware. We define the cross-Kerr coupling term between the CAT and the transmon. We set up the drive instructions on the transmon and the CAT. And then we instantiate the new model class for the tomography protocol for the involved subsystems and the coupling. Next in this block of code, we show our capability of defining a realistic generator within the Cruise toolset that is chained to the different drives in the model. We define a pulse envelope with no drive to be connected to the transmon for simulation of the controlled phase gate, while we define a square pulse to be connected to the cavity for the Kerr correction drive. We also define a pulse carrier associated with the local oscillator for our realistic control stack. Now, we create an instruction that connects the no drive envelope to the transmon drive and the square pulse to the cavity and the corresponding pulse carriers. We then instantiate the parameter map and the experiment object. We define a function that creates a sequence where the Ry pi by 2 gates in the Ramsey are treated as instantaneous unitary operations before and after the delay time, while our simulation will only show the state evolution during this delay time, which is typically of the order of several microseconds. To observe the state evolution, we define the initial state as the Kronecker product between the ground state and the transmon, and the CAT state extracted from the state preparation protocol. We visualize the evolution of the partially traced out CAT states during the tomography protocol. It shows a full 2 pi rotation during the delay time of the Ramsey sequence applied on the transmon. Next, we see if the readout reads the ground state of the transmon, the corresponding unoptimized odd CAT state can be extracted from the post-selection process. And post-selecting on the excited state of the transmon results in extracting the unoptimized even CAT state, as shown in this plot here. As expected, the even CAT state has higher phase space amplitude compared to the odd one. And next, we show the optimal control of the drive pulse connected to the CAT cavity, enabling Kerr correction of the extracted CAT states. We use the grape method with piecewise linear pulse shapes for the drives and allow for optimization of the in-phase component of the drive pulse connected to the CAT cavity. Then we create a new experiment object, compute the propagators, and instantiate the optimal control class to minimize the density matrix overlap as its goal function for the infidelity measurement, spanning over the subspace of the transmon and the cat states. We use a gradient-based algorithm for the optimization task again, and after this optimization run, we visualize the optimized pulse shapes for the Kerr correction drive, as shown in this plot here. The corresponding Kerr-corrected odd and the even cat states are also shown in this Wigner plots. This completes the simulation of the Wigner tomography protocol for the cat states. I would like to highlight that our modular CRUISE toolset is capable of building digital twins of complex quantum hardware systems, such as that of the dissipative cat qubits. Our toolset also provides optimal control solutions for pulse level control of these qubits. And in the next videos of cat qubits, we will show optimal control of single qubit gates and 2-qubit entangling gates. Stay tuned for more fantastic cats and how to control them using the CRUISE toolset. Thank you.